So, dear participants, we are here again in our third meeting of our colloquia on portable XRF X-ray fluorescence that is organized by the Global PXRF Network and the European Academy of Science and Arts STEMAC Expert Group. For our academy, this is a follow-up on a specialized section of the successful colloquia Arts Meets Science. And we would like to invite you also, all of you, to contact us to present your own topics, if you like, that you are dealing with in your activities on one of the coming colloquia. Also, myself and Michaela wish to express our gratitude to Keelie and Doris Klida for their immense technical help in organizing the colloquia. Today, I see once more our president, Professor Klaus Mainzer, which is with us, and I wish to invite him to greet today's colloquium. Dear Klaus.
You're muted. You might need to unmute yourself. I'm sorry.
Now I can start.
Yes, sorry.
Again, welcome to you all, and greetings from the whole Academy as president, and welcome to this further colloquium of the European Academy on portable X-ray fluorescence. Now, this week also marks the start of the Academy's summer semester of our Arts Meet Science series of events next Friday, and you are all cordially invited to attend. All these events emphasize that we are a working academy. The interdisciplinary profile of our events, which build bridges between the various academy classes, is typical, not only arts and sciences as next Friday, but also history, humanities, and technology as this evening. Tonight, we will see once again that the great and well-known advanced civilizations, such as Athens and Rome, did not fall from the sky and appear all at once. Rather, they were prepared over centuries in an historical and even prehistorical evolution. Their documents do not only appear in magnificent palaces and temples, as they have been known for a long time and characterize our view of history. Often there are also no written documents available. Modern technical, physico-chemical measurement methods are only now making it possible to open them up and visualize them using modern digitalization and AI. Even indigenous peoples who seem to have been forgotten in the darkness of history are thus coming back to life. An extremely fascinating stage, I think, in the cultural development of mankind, which is becoming visible through technology and can change our view of the world. I wish you a fruitful event and thank you for your attention.
Thank you, Klaus, once more for your support. Thank you. Today, we have two speakers, Dr. Johannes Sterba and Dr. Riehle, and I will try to present first speaker, Dr. Sterba, and then Michaela will present the next speaker, and at the end we shall have discussions to both of them. So the title is Local Pottery Production and Imports of at Monte Lato, which is in Sicily, and Chemical and Archaeological Perspective. Dr. Johannes Sterba is an interdisciplinary scientist. He is head of the Center for Labeling and Isotope Production, TRIGA Center Atominstitut, in the Technical University of Vienna in Austria. His PhD was application of neutron activation analysis to create a chemostratigraphy of a volcanic eruption sequence on Tilos and Niceros in Greece, and several actually papers on Greek archaeology. This is another point of his academic work that has attracted my attention actually. His research interests include archaeometry, chemical analysis, provenancing, statistical methods, neutron activation analysis, reactor physics, nuclear safety and security, with dozens of papers and significant projects on research in archaeology and natural sciences. My dear namesake, Ioannis, by the way, I liked your motto, looking for patterns in the pattern. The digital podium is yours.
Thank you very much. And thank you very much for the kind introduction. I wasn't expecting to hear the name of my PhD thesis again, which brings back very fond memories of great times. I feel like I should apologize a little bit because I will be presenting on neutron activation analysis on a colloquium on portable XRF, and I know that there's some dissonance here. But this is what Michaela signed up for when she asked me if I was happy to present here. So this is what you have to deal with tonight. I will give, and you probably saw that we have a common title. Kai and I are working more or less on the same material, the same presentation. I will give the methodological introduction or the chemical perspective, and he will follow up on the archaeological perspective. And as you just heard, I'm a physicist, so my archaeological perspective obviously is very, very limited. And if I make any archaeological mistakes, they are mine and not the ones of my cooperators. So please, I apologize for those right away. Let me just see if I can get this to work. Yes. I will give you an introduction into neutron activation analysis. And again, I apologize if you already heard about it, but I want you all to be on common ground on what it is and how it works, so that we can work from this. And then I will give you an introduction into the statistical interpretation that can be used and the statistical interpretation that I use for most of my work. And then I will introduce or move us into the Sicilian situation, which Kai then obviously will be talking about a lot more. And I will introduce you to the chemical part, and then he will take the archaeological part. Neutron activation analysis. It's actually a fairly old method, but it's still available in Europe. Unfortunately, not on that many facilities, because the use of research reactors has decreased a lot in the last couple of years. Why is it fascinating, and why do I like it, and how does it work? Essentially, radionuclides, which are atoms that emit ionizing radiation, by emitting this radiation can be very easily detected and identified. So we can do a qualitative analysis telling us which radioisotopes we are looking at just by looking at the type of radiation that is emitted. And you probably heard some of those. There's alpha decay, beta decay, gamma decay. We can look at the half-life of the isotope we are measuring, or just at the energy of the radiation we see, and we can identify the radioisotope we look at. And we can more or less at the same time do a quantitative analysis by looking at the amount of radiation we see, or the activity or count rate that we measure. This is very nice to work with, and it helps a lot in analytical methods. The problem, and the nice thing is that most radioisotopes can be identified by their gamma radiation, which is very easy to measure. And I don't want to go into too many details about gamma radiation, which is very similar to X-rays, just usually slightly higher energy. The problem, if you want to call it that, is that not everything is radioactive. Most samples that we encounter are non-radioactive, which is probably a good thing for the archaeologist excavating material that is not radioactive. But for the analysis perspective, it's not so good. Radioactive material is much easier to analyze than non-radioactive material. However, By using nuclear reactions, we can make radioactive common matter, most materials, and in most cases we use neutrons for this activation. So that's why we call it neutron activation analysis, because we use neutrons to make something radioactive, and then we can analyze it much more easily than we could in most other ways. Again, I'm a physicist, so you have to bear with me for a few slides on physics. The activation works in the way that we use the stable isotope. In this case, we are talking about sodium-23. That's the stable isotope of sodium. We all know sodium, right? This morning for breakfast, you probably had some eggs with sodium chloride. That's sodium right there. If we add a neutron to that, and that neutron should have a certain energy, but that's not so important. If we add a neutron to that, then sodium-23 becomes its isotope sodium-24, which is a radioisotope. During that reaction, a gamma photon is emitted, which we call a prompt gamma photon or prompt gamma radiation, because it's emitted during activation. So right at the moment that the neutron hits the nucleus of the sodium-23, we receive a gamma photon. That's slightly harder to measure. However, the sodium-24 itself is radioactive, so it's not stable anymore. However, it still tastes like sodium. It has the same chemical properties as the stable sodium, but it's radioactive. The nucleus is unstable, and it decays in a so-called beta-minus decay into magnesium-24. So now we change the composition. It's a chemically different thing now. It decays by emitting a beta particle, but also a gamma photon. And this gamma photon is emitted after activation at a later time, so we can measure that much more easily than the one during activation. Almost the last physical slide. This is a decay scheme of the nucleus of sodium-24. And I only show you this because it's important to realize that the sodium-24 we just created decays in a beta-minus decay into magnesium-24, which itself is stable. However, and this is where it's very similar to XRF, the nucleus now is in an excited state. Very similar to XRF, when you hit your shell of your atoms with X-rays, you lift electrons to a higher excited state. The same happens here, however, it happens with protons and neutrons. So the protons are at an excited state, and when they de-excite or relax back into ground state, we get some photons. So the gamma photons are emitted from the nucleus of the atom, but in a very similar way to X-rays, which are emitted from the shells of an atom. And because we have a difference in energy levels between shells and nucleus, gamma photons usually have a higher energy than X-rays. So in this case, you see those two photons that are emitted in this reaction are on the order of 2 and 3 MeV, mega electron volt, and not keV, which is the more usual energy range for X-rays. All right, so now we know how it works. We activate our material by hitting it with neutrons, then we receive some radioisotopes, take those radioisotopes, put them on our detector, and then just measure what's coming out of there. And by looking at the energy of the gamma photons, we can identify the isotope we are looking at, in this case, sodium-24 or whatever else we are looking for. And by looking at the intensity or activity of those gamma emissions, we can measure the amount of these radioisotopes we are looking at. And you see here the activation equation that tells us how much activity, how many gamma photons we expect to see after an irradiation under certain conditions. This enables neutron activation analysis to make a direct measurement. No comparators needed. We can just measure a sample and then just from looking at all those parameters, calculate the total amount of isotope we have produced. However, this is really, really painful. You can do it, and there are people who do it in the world, but it's very complicated. You have to characterize your reactor very well. You have to know your neutron flux density very well. You have to characterize your detectors very well and very closely. So this is hardly ever done in applications where you want to do a large amount of samples. This is done at special facilities that work at very, very high precision for very specific isotopes. But in general, that's not what we do. We make it much easier. We do comparative measurements. So we irradiate something of a known composition and compare it to the sample of unknown composition. And if we make this in a very clever way, and obviously we are very clever, so this is easy to do, this all reduces down to this very, very simple equation. The count rate we see from our unknown sample over the count rate we see from our reference material equals the amount of material of sodium, of chromium, of iron, whatever element we are looking at, over the amount of, over the known amount in our reference material. And as you see from this equation, one of those four variables is known, which is the mass in the standard reference material. The two activities, the two A's, are what we measure, and then it's very easy to solve this equation for the one unknown variable. Very simple thing. And I usually take my students through the whole thing, and then I show them this equation, and then they are very happy because they feel, okay, this is something I can understand and actually do myself. So this is how we do it. We do comparative measurements, and the result of such a comparative measurement is something I tend to call chemical fingerprint, and I don't want to go into too many definitions, and there's different considerations what a chemical fingerprint might be. In this specific case, please just allow me to call it chemical fingerprint. What I mean is we measure up to 30 elemental concentrations in our sample. Elemental concentrations means I know the amount of sodium as a concentration in our sample, so in micrograms per gram or in percent. The same for iron, the same for antimony, and so on and so forth, up to 30 elements. And that's what I call the chemical fingerprint. Now it gets worse because I'm taking you out of physics into math, which is always worse. Mathematically, if we look at such a chemical fingerprint, it's analogous to a vector or to a point in space, right? You know that I can define a point in my in my apartment by telling you how many meters you have to go into the apartment, how many meters you have to go to the right, and how many meters you have to go up, which is usually not more than 1 meter. And then I can point one specific point in my apartment out to you. Those are 3 coordinates, and they are very randomly because you start at the door of my apartment, but we can abstract it to just setting something to 0, and then I tell you there's the X direction, there's the Y direction, and then there's the Z direction, and then we can define a point in 3-dimensional space. Up to here, that's somewhat familiar. If I take you into concentration space, we suddenly have to deal with 30 dimension, which is unimaginable, but that's what math is for, right? If you can think about it, we just do some calculation, and that's usually how it works. So one sample, one measurement corresponds to a point in space, and however that space might look, 1 point in space. So 2 samples are 2 points in space, and suddenly if we want to understand or think about how similar those 2 points, those 2 chemical fingerprints are, we are just looking at how far apart are those 2 points in space, right? Because if it's the very same composition, if it's the very same chemical fingerprint, the points are identical, which will very hardly be the case because usually 2 samples do not come out as exactly the same. But even if they come out as slightly different, they will be very close together in space. And if one of those variables, or 2 or 3 or 4 or 20, are off, then they will be further apart and even further apart. So just by measuring or calculating the distance between 2 points, I can tell you how close, how similar those 2 samples, those 2 chemical fingerprints are. Sounds rather complicated. And because we have many variables to deal with, we need multivariate statistical analysis to deal with all those numbers, with those large numbers and many numbers. And because we are looking, and this is something you are very familiar with, because we are essentially looking at, I like to call it mud, but that's not a good word. But essentially, we're looking at geological material. We need some chemical and geological knowledge to figure out if something is similar because of chemical reasons or because of real provenancing issues, because it's really similar for other reasons, right? We all know that chromium and iron usually go together. So if a high iron and a high chromium value goes together, that's no big surprise. So this is something we just need to be aware of and take into consideration. Now, there's a few traditional methods, and obviously I don't know all of them, and I will not mention all of them, but I'll mention a few traditional methods to work with comparing ceramics to each other and finding out if they are the same or different, or figure out their provenance, where they are from, and similar. The maybe most traditional one is microscopic investigation or petrography. You're all familiar with that. From this, we can gain very nicely regional information. By looking at the mineralogical composition of our samples in a thin section, we can figure out what grain sizes, what types of minerals are found in our ceramic, and compare that either to other samples or to the general regional geology, and decide, well, this cannot be from here because there's no rounded quartz in here, so it has to be, it must have been produced somewhere else where they found this nice rounded quartz we see in our material. Now, this again leads to regional information. It needs an expert on petrography and the regions, because you need to have someone who has looked at a sufficient number of thin sections to be able to make the claim of something being similar or not, and identify the different minerals. And the clay matrix itself is not very helpful in petrography because it's very homogeneous. It doesn't tell us anything about its mineralogical composition. We can only look at the grains that are in there. And fairly unfortunate, depending on who you talk to, is that we need fairly large samples to get a good thin section, right? We all know that depending on the method you use, we will usually need to take a bit of sample. For petrography, we're usually talking about on the order of a centimeter or two that we need to actually get a good thin section. When we take it out of this microscopic investigation and move it slightly towards a mathematical statistical space, there's a very easy method of comparing two chemical fingerprints, which I call direct comparison. So we just take the differences of all of the elements that we measured, of all the concentrations we measured, and just look at them. And if all the differences are zero, then we are talking about the same sample. And if the differences are small, then we can claim that they are very similar. If the differences become large, obviously we're talking about different materials. In this case, the scaling is very important, right? Because if we compare two iron values, which are on the order of %, and just compare the difference between those, the difference can be large, but not very important on the order of magnitude. Whereas, so a difference in iron of, I don't know, 0.5% is maybe less important than a difference in chromium of 5 ppm. So just comparing those two numbers, we see that we need to think about how we scale those different concentrations. And it's a manual piece-by-piece comparison, right? You have to take the differences of two samples, those two samples, this sample against this sample. So if we talk about 500, 600 samples, this gets tedious very quickly because we can't look at that many numbers, at that many graphics, and it's not a statistical evaluation. At the end of the day, we're just looking at structures, at nice, maybe a graph or two, but it's not something where we can say, well, this is a significance of 0.5, so we take it as a good value. Just as a quick example, this is a very easy comparison of two samples, and you see I just did this calculation, subtracted every concentration value of those samples, so the cerium concentration of sample 1 minus the cerium concentration of sample 2, and so on and so forth, and then I get this picture. And just from looking at it from somewhat of a difference, you already see that there are largish differences in zinc, in uranium, in thorium, in scandium, and in hafnium. So we would probably not believe that those two samples are the same. The scaling on the y-axis in this case is with the measurement error. And I will get to that in a moment anyway, but just so you are aware that those samples are all scaled to their individual measurement error. Now, another traditional method, now we're moving into real statistics, is the principal component analysis. And we are probably all familiar with that. It's a very nice method. I'm just reading a very nice oldish book on statistical methods and how they develop. And if you read old statistical papers, you will find usually an appendix that explains to you how to do calculations on a manual calculator. Right? Very old people, well, very old methods. They did not have computers available, so they had to do all the calculations by hand, which is extremely painful and makes multivariate statistics almost impossible. Nowadays, we have computers, we have very nice statistic packages. Even Microsoft Excel can do statistics, even though it usually lies. Don't believe in Excel. However, you can do statistical analysis very easily because our computers have huge calculation power. Principal component analysis, and I believe you are somewhat familiar with the concept, essentially tries to turn this cloud of points in multidimensional space and to see where the largest variances come to lie on which axis, and then we can get, for example, a good visual representation of our samples. Again, scaling is important. Many methods do some type of scaling. You have to think if they are correct or if your data set needs a different type of scaling. And it's very nice to look at coarse structure in your data because you can very quickly see that there are two very obviously different groups of samples in your data set, and that helps a lot. However, it's an explorative method. It does not give you a number or a percentage of probability, how likely it is that one sample belongs to one group or another. You have to come up with your own measure of likelihood in this case. PCA only helps you in rotating your cloud to make structure visible. Just simple example, those are I think 20 samples or so, maybe a bit more, of 3 different ceramics. I did those myself. Those are experimental pieces, and you see that the red dots, which are the untempered clay, the raw clay, that is obviously very different from those 2 tempered clay groups, the green ones on your right and the blue ones at the bottom. So this is just the raw PCA, and we actually see a very nice distribution of groups. That works nicely. Cluster analysis, actually very similar to PCA if you think about it long enough, but it works slightly differently and gives different pictures. Again, it's a method of looking at distance in multidimensional space and calculating this distance and then grouping your samples. The closer they are together, the closer they are grouped together. This strongly depends on how you calculate distance in space. We all learned in school to calculate something we call the Euclidean distance, which is, if you remember and are not too scared of it, the square root of x squared plus y squared plus c squared. That's the distance in Euclidean space, and that works fairly well. However, you have to, that only works in Euclidean space, which means that all axes have to be in at the right angle to each other. In cluster analysis, you also have to define some kind of cutoff. You have to define what distance is close enough to claim that the samples belong to each other, and at what distance I believe that the samples do not belong to each other. And again, it's an explorative method. And I'll show you the same set of samples I just showed you in the PCA, now as a cluster analysis. And you see that on your right-hand side, there's the samples called T something. Those are the untempered clay samples. Then there's the group of B samples that nicely groups together again, which are the ones that have some basaltic temper in there. And then there's the S and ME samples that contain quartz sand as a temper. And you see that they nicely group into the 3 groups we just saw earlier in the principal component analysis. So those 2 methods can yield the same results. not necessarily every time, but in this case, they do this nicely. However, if you think about this cutoff I just mentioned, where do we cut this tree, this dendrogram? If we cut this tree at 5, at the distance of 5, and you try to draw a horizontal line at the height of 5, you will see we only get 2 groups, right? We only get the quartz sand tempered, the S and M pieces, and the B and T pieces come together into one group. If we want to get the 3 groups we saw earlier, we need to cut it at slightly below 5, which is probably 4 or 3.5. Then we get those 3 groups. If we cut higher, we get less groups. If we cut lower, we get more groups. And this is essentially up to you. If you know what the groups are supposed to look like, it's very easy to find a good cutoff. If you don't, then you're left at guessing what a good cutoff might be. Now, those are all traditional methods of multivariate statistical analysis and have widely been used in the analysis of chemical fingerprints of pretty much anything, but also ceramics, obviously. Now, ceramics specifically is kind of a special case because it's not a straightforward natural material. As Ioannis so nicely mentioned before, my first experience or my first in-depth analysis using neutron activation analysis was on the chemical composition of volcanic material. And this is much more straightforward because there's no interference of someone who tried to produce a product for a specific case. But in volcanic material, you just have the material as it comes out of the earth. And you just take it as it is. And pumice does not change its chemical composition and is not changed in its chemical composition. However, in ceramics, we all know that the production of ceramics needs at least some kind of recipe. It needs to do something to the clay, some cleaning, some tempering, at least some washing, some firing to produce a workable and usable ceramic vessel that is then later used in whatever, cooking or something else. Now, if you imagine, and I like this example very much, I apologize that the time is not right. If you imagine baking cookies at home, right? But you can also do pasta, same concept. What you do is you produce a dough following a recipe, right? So you take the dries and the wets and you mix them up. And then you start kneading your dough until it feels right. And even though you have a recipe and you know that you need that amount of flour and that amount of water and that amount of fat, once you knead the dough, you realize, I need a little bit more flour. I probably need a bit more water for this, maybe a shot of milk. And then you just work your dough until you have something that works, that feels right. And then you start forming your cake, your cookies, your pasta, whatever. I prefer pasta, by the way, to cookies. And then you cook it, bake it, and you're done. And something very similar happens if you work with clay and try to produce ceramics. You have a recipe, very obviously, because people were working with fairly precise recipes. However, depending on the day, depending on the wetness, depending on the humidity, you will maybe add a little bit more sand, a little bit more water, and work your raw material, your paste, until it fits perfectly to today's conditions. So minimal changes between batches of prepared clay can be expected. Minimal changes, nothing big, but there might be some differences. And we can also expect that one location, one workshop, one village, whatever you want to call it, will use more than one recipe depending on what they want to produce, right? If you want to produce something very fine, very thin-walled, you will need a different recipe than if you want to produce a vessel with thick walls that can be fired and not break during firing. So more than one recipe is imaginable, and there might be changes within the recipe between batches, between Monday's recipe and Wednesday's recipe. So if possible, it would make perfect sense to group by recipe, right? If we can get this resolution, if we can get fine enough to see different recipes in use, that would be really nice. We kind of lose the correlation to the raw clay, to the raw materials, because the recipe is a change from the raw material. However, we learned something about how the workshops worked, how they used the recipe to create specific types, specific forms. However, for this to work, we need to overcome those between batch variations, because if we see those two, then we get many, many, many tiny recipes that don't make any sense at all. So this is something you have to keep in mind if you work with ceramics. Then in the 80s and maybe earlier, people came up with something they called the best relative fit factor. And this is exactly what I try to explain with what I mean with overcoming this in-between batch variation. It is sometimes explained as calculating out the temper, but that is too simply explained and doesn't really cover what this method actually does. Between batches variation, right? You just add a little bit more flour to your dough for your cookies. You add a little bit more water, a little bit more salt, whatever. It mostly comes down to an in or decrease of something like quartz or maybe grog or maybe something that doesn't really change anything off, and that's important. It doesn't really change the elemental composition. You will probably not just add in some indium or some iron, but just a bit more sand, a bit less sand, something like this. But it will change the total mass, right? If you add more sand, the total mass of the sample will change. And that means that the concentrations, all of the concentrations, will either move up or down, right? If you think about your dough for making pasta, if you add more salt, then you change the concentration of salt. However, if you add more flour, the concentration of salt will decrease, because in total, you will have less salt per mass. This is exactly what happens. Now, for this, we can compensate, because we can compensate for something that changes all the concentration values in the same direction, all of them upwards or downwards. And this is what this best relative fit factor actually means. And if we do this, if we do a correction like this, we still are compatible with multivariate statistical methods. Because we didn't change anything, we just removed 1 degree of freedom, and we moved the concentration space. We moved the point slightly along in concentration space. I'll show you in a second. Now, best relative fit factor. I'm back to kind of mathematical graphs. To make it easier on your eyes and mind, and honestly also on my mind, I take us out of 30-dimensional space and I move us into 2-dimensional space, right? Because this is something that we can actually work with. But everything I tell you now also works in 30-dimensional space. It's just not possible to think about it without getting brain fatigue. Now, 2-dimensional space, we have 3 points, right? We have point A, point B, and point C. And those points are defined by, in this case, their potassium and their sodium concentration. And I just choose those as complete random. It doesn't make any like real life sense. Just needed some points to show you. Okay, so those points are here. Now, the distance between point A and point C, as you see here, is 2,500 units of measure, doesn't matter. And the distance between point A and point B is also 2,500 units of measure, okay? So now we would believe that there's an equal probability that A and B are the same or A and C are the same. If we, however, believe that points B and C could need something like a best relative fit factor, that means mathematically that we can move those points along a line as long as this line also hits the origin, the point at 0, 0. That is all this best relative fit factor does. It moves the point along a line that goes through 0. If we allow for this, we can minimize this distance, right? We can make a calculation of how far do I have to move the point B, that it gets as close as possible to point A. And we do the same calculation for point C. And if we do this, we get those new points in turquoise, B corrected and C corrected. And you see that B suddenly is much closer to A than C. C essentially stays at the same distance. From 2,500 to 1,600, it's still rather far away. However, B suddenly comes much closer. And this is because we allowed for the best relative fit to do its work. Now, again, don't try to imagine it, but this also works in multidimensional space. We can do those calculations easily in high dimensional space. And if you want to do it, it looks like this. That's the modified Mahalanobis distance that can actually do all of those calculations I tried to explain in the last couple of minutes. And it was more or less invented or established in the 80s and 90s by Mommsen and Bayer later on. And it is a distance measure. That's important. Remember, I said that when we consider those samples to be points in multidimensional space, similarity becomes distance. The closer, the smaller the distance, the more similar two samples are. And if you look at this equation that's up here on the screen, you can see that we have this F0 in here, and it's next to the X on both sides and next to the SX in the middle. And this F0 is exactly this best relative fit factor that allows me to move X along an axis to get it as close as possible to Y. And it also thinks about the scaling. I mentioned repeatedly several times that it's important to think of scaling, and SX and SY are the measurement errors or the variation of a group. So our scaling is done by how good can we measure one concentration, and we allow for the best relative fit factor, and then we get this, to my mind, beautiful equation. The beauty about it is it comes out to one value, right? I can compare two samples, two chemical fingerprints to each other and calculate one value. And this one value is chi-square distributed. So it follows a statistical distribution, which means I can test it. I can do a statistical test and say, now, if those two samples are completely random, how large is the probability that my D, my total number, comes out to be so small as it is right now? And if this probability is very, very low, I can conclude that those two samples are not randomly at their distance, but that they are actually come from the same sample space. So they are actually from the same chemical group. And if this probability is very high, then those samples do not belong to each other, and we need to separate them. Essentially, and that's taking it very roughly, if this D squared on the left-hand side of this equation comes out to be 2 or less, then we can claim that those two samples are actually the same with an error probability of roughly 5 to 7%. That's very convenient because now we can do all this comparison, all this calculation. We can let a computer handle it and then just look at the numbers and sort it by smallest distances. And we are very quickly done with figuring out what samples belong to the same chemical group. Looking at it from the PCA perspective, in this case, I'm using a principal component analysis only to make something visual that actually happens in multidimensional space, right? Every sample you see here is, as I mentioned, a spot in 30-dimensional space. But to make it visible, to make me able to show it to you, I have to somehow project it down onto a 2-dimensional plane because otherwise our computers would explode. Now this is, you've already seen this, right? So we have the red ones, which is the untempered clay. We have the green ones, which is the quartz tempered clay. And we have the blue ones, which is the basalt tempered clay. And we see those three groups. Nothing happened here. Now I do this calculation, right? I say all the green ones belong to one group. So I find the best relative fit factor for all of them to come as close to each other as possible. Same for the red ones, same for the blue ones. If I do this, bam, all the groups are much smaller. This is nice and as expected, so the calculation works, but it doesn't really help us, right? Because it's still, well, okay, so now we still have three groups, they just look more nicely, nice enough. However, if we do this best relative fit calculation before the grouping, before we decide which belongs to a group, and then do the calculation and then start the grouping, we see this picture. We suddenly get 4 groups, We still have the blue group, which is the basaltic tempered stuff. We still have the red group, the raw clay, but very close to the red group, we see one of the green groups, the group of green triangles. And the green triangles are samples that have been tempered with quartz sand, however, with quartz sand from the Saharan desert. And the green ones on top, the other green group, are samples that have been tempered with quartz from a local construction site. Okay, and suddenly there's a difference between those two, which is very interesting. And if you look at all the numbers and dive very deeply into the chemistry, you would see that the Saharan desert samples actually contain a mineral called zirconium. And that's why we can see a difference, and that's not contained in the construction site sand, and that's why we see a difference. And we were not able to see this very, very small difference in the original data set because all the variations that come into the recipe, the creating of the tempers and the working of the clay were larger than the small difference between those two zirconium and hafnium values we see that separate those two groups. So only by allowing for the best relative fit factor, we were able to separate those two groups, even though, and I produced those samples, so I know how much effort I put into getting the right recipe for all the samples. And there's still this variation in there. Okay, I hope I could somehow make you believe me, at least for another 10 minutes or so, because now we move into the Sicilian situation. Okay, so this is like, now I'm playing volleyball and I'm playing the ball over to Kai. In Sicily, things are chemically a little bit strange, at least from my perspective. I have a set of almost 300 samples that were collected, obviously not by myself, but by colleagues from all over Sicily. For some reason and for the types of cooperations we've been working in, and there's also some work of Hans Mommsen in here, obviously. They are predominantly from northwestern Sicily, but we also have a few samples from eastern Sicily and from southern Sicily. And actually, there's 2 or 3 samples in there that were found on Malta. The samples roughly span from the Bronze Age to the Iron Age, but again, Kai will talk to you about how this works, and I'm a physicist, so I'm happy that I'm able to say those words, but I don't really know the meaning of them. However, chemically, we get a very, very complex picture. We see several chemically very similar groups that are close to each other, that sometimes overlap, and that are no fun to work with. Okay? Just to show you how this looks. This is the data set of the 300 samples, and I plotted in the 5 different Sicilian groups we are working with right now, and you see that you don't see anything, right? There's large overlap. You can kind of guess that the red dots, the Himera group, is on the upper part of the graph, and the blue ones are to the left, and the green ones are in the middle, and the violet ones are further down. But there's no real clear picture that we can work with. Okay? However, again, if we apply the best relative fit factor and take some time and work through that and try to figure out which samples are closest to each other, and from this iteratively build our groups, the picture becomes much clearer and looks like this. And I know this is hard to believe because I'm clicking and then suddenly I show you a different picture. But this is the same data set, just allowing for the best relative fit factor. And you see that this comes out fairly nicely as 5 different groups that are separated in space from each other. And again, this is just a visual presentation in 2 dimensions, and the real space is much larger and a bit more complex. However, you see that we see 5 different groups, and this looks much more usable. Now, and this is important to me because I encounter a lot of confusion about this part. Those are chemical groups. So my only claim is that those samples chemically are sufficiently similar that statistically I need to put them together because they cannot randomly be so close to each other. Okay? I make no claims whatsoever about archaeological meaning of those groups. Just chemically, they come so close to each other that I need to group them together. Now, this means that in this chemical grouping, we heavily need to rely on the best relative fit factor. I just put the figure down here again, smaller, so you can follow along with what I need to say. The interesting thing is the main difference we see between those 5 groups are all in the trace elements, and all in the really trace elements on the order of 1 to 10 micrograms per gram concentration. So we're talking about very, very minute, subtle differences that you would not see if you only look at potassium, sodium, iron, and maybe scandium. You need to look at the very, very traces. And you need to have a good resolution and good and high reproducibility to actually see that. And one more thing I would like to point out, but I also mentioned that this is still a point of contention between me and other archaeometrists and archaeologists. All those 5 groups come in concentration space, come to lie on a straight line. It's not as obvious here as it would be if I added another dimension, but you can probably imagine that. Those 5 groups look like pearls on a string. Okay? This might be random, however, it could indicate that those 5 groups are actually a mixture of 2 hetero-unknown concentrations or points in concentration space. And if I mix them 10 to 1, I get the blue group. And if I mix them 1 to 10, I get the red group on the right-hand side. And if I mix them 4 to 3 and whatever other mixtures you can come up with, I end up with the other groups in here. Now, I do not at all claim that this is an intentional mixture done by someone with an intention of confusing archaeologists at a later time. I can imagine that this is a natural phenomenon we're looking at. We could look at clay beds that come to lie atop of each other and then became mixed over time, or just by digging deeper through a clay bed or along a clay bed, you kind of randomly reach one mixture or another mixture. Something along there would explain from a chemical, from a geological perspective, why all those groups are so similar to each other. And you will see from Kai in a moment that they're not just chemically very similar, but they're also archaeologically somewhat confusing, at least to me. So with this, I would like to hand everything over to Kai, just for a short conclusion. It helps a lot if you have high precision for trace elements, right? If you measure only 5 or 7 or 10 elements, that's good, but it's better to measure a few more elements if possible, and high precision. And it also helps, and that's really important, to know your measurement errors for each element, for each sample, if possible. Because that helps you with all the scaling operations, and it helps you to decide if 2 samples or 2 numbers are actually within measurement error the same or not. That's an important thing to think about. But even if you make everything as perfect as you want, complex situations will appear. When you start out, you usually get a few groups and everything looks very nicely. And the more samples you get, the more groups you see, the more complex the picture gets and the harder it gets to see what's actually going on. And in my experience, and it's been a few years now, the most important part about working in this field and working on this edge between natural sciences and archaeology in general is close contact and a lot of trust between the sciences and the archaeologists, believing that the other person knows what they are talking about, but also getting the trust and respect that the other person also knows what they are talking about. If you work on this level, you can gain a lot of insight and work very nicely with each other. And with this, I hope I didn't take too long. I would like to hand over to Kai.
Michaela, can you introduce Kai?
Yes, thank you, Johannes. I have a lot of questions, but it's not the time now, because my job now is to introduce Dr. Kai Riehle, and I'm very happy to do that. He has an interesting career because he didn't start out studying archaeology right away, but he was trained in the crafts and worked there for a couple of years and then after that, he went to study classical archaeology at Tübingen. He was involved in a number of excavations, and as a student assistant, he already dabbled into the archaeometry methods, and then worked for his PhD on the so-called Greek colonization, and joined, after he finished his PhD, the Potter's Reaction to Local Demands, which was a project financed by the Austrian science funds. He loves to apply archaeometric analysis and is especially interested in processes of continuity and changes in material culture, especially pottery, and that, as he will tell us in the next minutes, in the context of pre-Roman southern Italy and Sicily. And with that, I would just quickly hand over and have Kai start his presentation.
Very much for this nice introduction. I just try to share my presentation with you. So now you should all see the presentation.
That's there.
It's there?
Yes, it is.
Okay, beautiful. Nice. Thank you. So first of all, of course, let me express my gratitude to the organizers of this colloquium for giving us, that is Johannes and me, the opportunity to present our results obtained by NAA against the archaeological and cultural historical context. And this is important insofar as, at least from an archaeological point of view, it is the context that ultimately justifies our application of such analytical methods as NAA. Keeping this in mind, I remember very well my first encounter with Hans Mommsen, that is the, let's say, father of the NAA, the Bonn laboratory, who right after saying hello told me that the archaeometrists only provide tables and numbers, and the archaeologists have to uncover their meaning. On the one hand, this statement, no doubt somehow somewhat exaggerated, makes a valid point. From an archaeological perspective, archaeometric methods, whether NAA or PXRF, are primarily a tool to answer questions that cannot be answered by a purely archaeological approach. At the same time, they might be useful to refine or modify our traditional, or rather traditional methods. On the other hand, Hans' statement, if taken literally, creates an image that, as I myself experienced, does not apply at all to his or even Johannes' way of doing things. As Johannes said, the relationship between archaeometry and archaeology is never just one of, let's say, ordering and delivery. At least it should never be like that. It is only by engaging in open and critical discussion that the particular strength of both methods and other disciplines come to bear, which also includes consideration of their respective limitations. Elsewhere, we have described this process in metaphorical terms as an interdisciplinary ping-pong match in which the ball passed from one side on the table is returned with a different spin. What is more, an additional view from a third methodological perspective might also be extremely useful, for example, that of PXRF specialists, a kind of mixed double then to stay with the ping-pong image. And it is not least for this reason that I'm really happy to speak here tonight. So during the next 30 minutes, I would like to follow up on Johannes and illustrate the ways in which the NAA could help us to better understand processes of social differentiation within ancient communities. And speaking of we, I'm referring to all the colleagues of our project. We heard it already, Potter's Reaction on Local Demands, funded by the Austrian Science Fund. All the colleagues listed here on this slide. Assuming that both consumption and production of material culture is bound to social practices and thus to the local social fabric, which in turn is influenced by non-local factors, we comparatively analyzed social transformations at 3 different sites in southeastern Italy and western Sicily, all based on local pottery production. The historical framework is set by the dialectic of a, let's say, shrinking Mediterranean world caused by increasing connectivity in the course of the first millennium BCE. That is the early Iron Age for Johannes. On the other hand, this kind of proto-globalization leads to phenomena of homogenization of material culture on a global, that is, Mediterranean scale, while creating local differences at the same time. Put another way, the formation of locality is closely linked to global processes, as has been highlighted in recent studies, for example, by Tamar Hodos and Hans Beck. With regard to southern Italy and Sicily, migratory movements from the Greek and Levantine areas are of particular importance, often referred to as colonizations, as in this rather simplified map. They are important because they certainly had an impact on the social composition and identity negotiations of the indigenous communities already present within those zones of contact, even though to varying degrees and ultimately depending on how much a certain community was involved in these contact situations. Our project now aims to trace these impacts by a contextual evaluation of the pottery finds and to specify the role that local pottery production played within this process. Our rather simple basic assumption is that different local situations led to different local demands and consumptions to which local potters responded, well, differently. Today, however, I would like to limit myself to the results of just one of our case studies, which I think illustrates our approach and the fundamental role of chemical provenance analysis therein quite well. And this is Montiato, as you can see here on the slide, a hilltop settlement about 850 meters above sea level, right in the heart of Western Sicily, a region that has been a vibrant contact zone and, yeah, so to speak, cultural melting pot since the 8th century BC. Within a range of about 50 kilometers as the crow flies around Montiato, there are lots of indigenous inland communities alongside Greek and Phoenician coastal settlements, put in different colors here on the map, all well connected by river valleys to the interior. Testimony of these contacts and connections is provided by the finds of Greek pottery among the earliest evidence of a settlement on that hilltop, dating back to the 7th century, when the site consisted just of scattered clusters of circular huts, small hamlets. In the course of the 6th century, contacts, especially with the Greek neighbors, intensified, as is indicated by a strong increase in the number of Greek-style drinking vessels found, particularly in contexts associated with an elevated social status. These contacts culminated in the late 6th century when Greek, or rather Mediterranean, cultural influences turn out to be evident also in architecture. For example, in the Western Quarter, an earlier cult site has been transformed into a sanctuary complex, including a Greek-style temple, the so-called Temple of Aphrodite. Subsequently, a two-story building with banquet halls has been built to its west, the so-called late archaic house, likewise heavily influenced by Greek architecture, bottom left. Further oikos-like buildings, that is houses that could also be described as drawing on Greek models, follow to the east of that house. And I'm placing particular importance on this area of Montiato because most of our sampled pottery was found here. However, before I go into detail, I would like to briefly summarize the subsequent pre-Roman settlement history. It is around the middle of the 5th century BC that there's clear evidence of a significant turning point. The buildings already mentioned were ritually destroyed and sealed. The entire settlement appears to have been largely deserted. And it was not until 300 BCE that the site experienced a revival, taking on the appearance of a now true Greek polis with the construction of huge public buildings such as the Agora, Stoai, and the theater, as you can see here in the picture bottom right. From this point onwards, the settlement is also known by its Greek name Yaitas. Following the end of the First Punic War in 241 BC, the area, along with entire Sicily, was finally incorporated into the Roman Empire and marking the end of our very brief history of Montiato, even though settlement continuity actually extends right into the Middle Ages. Having that been said, we now turn finally to the pottery analysis. As already mentioned, our aim was to uncover the different effects of increased connectivity by means of locally produced pottery. The underlying requirement for this was the identification of the local production spectrum on a base as broad as possible, which in turn implies the determination of one or more chemical local signatures or even fingerprints. Unfortunately, there are no direct remains of ancient pottery productions at Montiato, as is the case for many other sites. So neither potter kilns nor dumps of pottery waste or misfires have been uncovered so far. So it means that we have no clear reference material to determine the local chemical fingerprint. Therefore, local reference had to be done on the grounds of other evidence, and in the first place, a typological selection as broad as possible. This includes, for example, loom weights, kitchen and coursewares, architectural ceramics, and pottery types for which a local origin can be assumed for statistical reasons. Of course, these are rather weak reference markers, and each of these wares, from loom weights to kitchen pottery, could also be imported on a large scale. In their totality, however, corresponding import patterns should arise in such situations, which, as we shall see, is not the case. In addition, we also expected to draw conclusions from the distribution of chemical patterns. For cross-checking, we have also sampled pottery that can be addressed as non-local with good reasons. So all in all, we sampled almost everything that we could get, albeit the supposed imports to a significantly lesser extent. Let me turn now to the results plotted here in a rather abstract way. We sampled a total of 378 ceramics, which can be assigned to a total of 22 chemical element groups. These include 47 singles and 9 pieces that each belong to a pair. These pieces do not fit to any identified pattern, what might be due to a variety of reasons, and they are of no further interest to us today. By sorting the sampled pottery according to their chronological range, we have thus 261 samples from the archaic period, that is the period up to about, let's say, 450 BC, here on the left side, and 117 samples from the Hellenistic period, that is the period from around 300 to the 1st century BC, here on the right side. So there's a ratio of roughly 2:1 in the sample size, which is also more or less reflected in the distribution of the loners. However, as said, we will ignore them from now. If we consider just the archaic period, 221 samples have been attributed to 16 chemical element patterns. One of these patterns here on the right side is yet A, and this pattern stands out in particular as it accounts for 45% of all assignable samples. Considering our sampling strategy, that alone raises the suspicion that the corresponding pottery is of local origin. And that suspicion is confirmed by looking closer to the pieces that belong to that yet A pattern. These include all types of wares that we sampled as local reference markers, even though weak reference markers if regarded in isolation, as already mentioned. Starting at 12 o'clock at the slide, we find clockwise construction ceramics such as roof tiles, next to loom weights, choroplastics and figural terracottas, hand-built kitchenware, and pitoi, that is large storage vessels with a height of up to 1.5 meters. Besides these, we also find incisa pottery, or so-called incisa pottery, decorated with engraved patterns, typical of what we might call indigenous Western Sicily, as well as dipinta pottery decorated with matte paint in a wide variety of shapes and quality. Another feature of pattern yet A is the so-called piumata pottery, which is less typical for Western Sicily, although most examples of this type of pottery were found at Montejato, but more on that later. And last but not least, we have also to mention transport amphorae. So long story short, from an archaeological point of view, due to the typological spectrum and quantity, everything points to Yad A as being a local fingerprint of Montejato. And this brings us to our second group. And don't worry, I won't go through each of the 16 groups, but will limit myself to those that are most relevant for the topic today. However, the second group is Yad B, which accounts for 10% of the total. And Yad B, sorry, that was one slide too fast. So we are here. No, it was right. Now we have it. The second group, Yad B, clearly displays a significantly lower variety of wares. So we have alongside the fragment of a transport amphora, a cooking pot and an ingesa vessel. First and foremost, Dipinta pottery, but all these types follow more or less the types that we found in pattern Yad A. So typical of the indigenous milieu of the Belice Valley region are jugs with painted birds, some more abstract than others at the bottom of this slide. Besides these, we find large mixing vessels with short horizontal wavy lines reminiscent of the letter W. To date, these vessels bearing this W-like decoration have only been found at Montejato, numbering around 25 pieces to date. We are therefore quite certain that Yad B was also produced at Montejato. Previously, Johannes told us that statistically, it's not always easy to split up these groups in northwestern Sicily, as is the case for a group in Himera or from Himera called Him B. So Yad B cannot be separated in a straight way from this Him B group from Himera. And Himera is just about 50 kilometers east of Montejato, as you can see on the map. So this raises the question of whether the Yad B pottery found at Montejato might have been imported from Himera, or whether the Him B pattern from Him B pottery from Himera actually comes from Montejato. Well, we think that several factors speak against both possibilities from an archaeological point of view. Firstly, Himera was founded in the middle of the 7th century by immigrant Greek groups, while the bulk of Yad B pottery is of indigenous tradition. Of course, that alone is not a compelling reason. However, very little indigenous matte-painted pottery is generally known from Himera and its surrounding area, which has been the subject of intensive fieldwork for more than 50 years. And hardly any of these pieces, most of which are large storage vessels, corresponds to the types we find in Yad B at Montejato. As mentioned before, the W-shaped decoration is found exclusively at Montejato. And the history of Himera provides us with further evidence. The city got destroyed and depopulated by Carthaginian troops in 409 BC and was never rebuilt or repopulated afterwards. However, we still find Yad B pottery in stable numbers at Montejato during the Hellenistic period, more than 100 years after the destruction of Himera. And we find it in types of monochrome domestic pottery that, based on macroscopic fabric analysis, have also been linked to a local, that is Yatinian production. Therefore, for these two main reasons, we believe that the Yad B pieces found at Montejato are of local production and were not imported from Himera. At the same time, we assume that just further systematic samplings at Himera will provide a better differentiation of the element patterns of Yad B and Him B. So again, the pottery of the patterns Yad A and Yad B should therefore be considered as locally produced. And despite less strong evidence, we would assume the same for the Yad C and Yad E groups. For Yad C, the related pottery matches that of Yad A in terms of type, and includes some large storage vessels, which is always a good identification indication for a local origin. Yat E, on the other hand, is mainly made up of hand-built and wheel-thrown cooking vessels, as well as a loom weight and terracotta hood model similar to that of Yat C. However, given the overall quantity of Yat E, its presumed local origin appears to be the least certain. Having now addressed the groups that we consider to be local, we turn now to those pieces that are definitely not local but were imported. And this includes, for example, the sherds that we sampled as a test group, so we have already assumed that these pieces are not local based on their morphological and typological features. In most cases, these are wares and shapes that can be linked to the Greek mainland. For example, as we can see here, several C-type black loss bowls, stamped dishes and small salt cellars dating all to the 6th to the 5th century. We see and pointing strongly to Athens due to the high quality of the gloss, firing and the characteristic fabric. From a chemical point of view, this Attic test group indeed exhibits a pattern KRPP that has long been known in the joint Bonn and Vienna database and can be securely traced back to Athens. Since pottery from Athens was widespread throughout the Mediterranean at this time, its presence at Montellato is generally not surprising, even if the vessels found their way most probably not in a direct manner, but via several stages. The same can be assumed for the appearance of some pieces of Corinthian pottery that's slightly older and dating to the 7th and first half of the 6th century BC. Here too, we sampled a few pieces and encountered the well-known Mübe and Mbe KK patterns. And these patterns, in turn, have been attested in Bronze Age misfires from the northeastern Peloponnese, and they are frequently found in Iron Age pottery of Corinthian style, as is the case for our pieces here from Montellato. So again, chemistry matches archaeology. So amongst others, it is the Corinthian and the Attic pottery that clearly indicates the community's early participation in exchange networks spanning at least to the central Mediterranean. Given the Western Sicilian setting of the site, this is not particularly new or somehow surprising. However, it does raise questions about the purpose of these imports and the local impact. And to address this topic, we first have to come back to the wares that has been produced locally. Based on observations of shape, type, and decoration, as well as the place of consumption, locally produced pottery at Montellato can be classified along 3 categories. These are traditional, traditionalist, and what we want to call a cosmopolitan. So what lies behind these classifications? Well, as traditional, we refer to the incised pottery or ceramica incisa that has been widespread in Western Sicily since the early Iron Age, with Sant'Angelo Muxaro considered an important center for an early period. In fact, this ware is a kind of leading fossil of Western Sicilian indigenous pottery between the 8th and the 5th centuries. A traditional line is also followed up by hand-built cooking vessels, which we have encountered in almost all local elemental groups, and which include the typical functional shapes of teglia and pinata, for example. For the Pinta pottery, a ware that became quite popular in many inland sites during the 7th century, the label traditional only applies with some restrictions, as some of the shapes and motifs clearly refer to Greek pottery. Nevertheless, the Pinta pottery of this period can generally be considered traditional. However, we have also examples of the Pinta pottery so close to Greek models that they cannot be classified as traditional, but were apparently intended to follow a broader, let's say, Mediterranean style of drinking vessels. In some cases, the similarity is so close that the pieces are hardly distinguishable macroscopically from pieces actually produced in Greek cities, as for example, cups with averted rim or Ionian cups, here on the bottom left, that were widespread during the late archaic period. Contrary to the term traditional, we therefore refer to this group of wares as cosmopolitan. Alongside cups with a weighted rim, this group includes colonet craters as well as jugs and stamnoi, drawing on Eastern Greek pottery in shape and decoration here on the right side of the slide. Another two dipinta cups of local production, both in their decoration and shape, refer to Western Phoenician types that circulated during the 7th and 6th centuries BC. What is interesting here is that these Western Phoenician types in turn resemble earlier Greek types dating back to the late geometric period, that is the end of the 8th century and the beginning of the 7th. In other words, a kind of diachronic dual appropriation that once again illustrates the melting pot character of parts of the Mediterranean material culture during the 1st millennium BCE, not only but especially in Sicily. However, the label cosmopolitan is not limited to drinking vessels alone. This is the case, for example, for a transport amphora of the Yad A group, which is in shape very close to Western Greek types. A similar piece was recently found at Entella, less than 30 kilometers south of Montellato, which, independently of our analysis, has been attributed to Argentinian production. Finally, we are left with the rim of a real-thrown hydra here on the bottom, a typical Greek cooking pot which differs in shape and technique from the traditional kitchenware that we have seen before. However, also this piece has been produced at Montellato. For the archaic Montellato, we thus encounter a pottery production spectrum that, in addition to the expected traditional wares, includes a rather unexpected variety of vessels that went beyond the traditional framework and were open to influences from the wider Mediterranean world. Creativity on the one hand, conservatism on the other. However, creativity and conservatism can also come together, as is the case with the pottery we refer to as traditionalistic. This is a hard term to speak. A good example is the locally produced Piumata pottery, which draws on much older models that were particularly common in eastern Sicily between the late Bronze Age and the early Iron Age. In the west of the island, however, this type of pottery was by far not as widespread as in the east. Nevertheless, a major find spot for these Piumata vessels in the west is Montellato. However, all in context dating to the 6th and 5th centuries BCE, what actually seems too young for this type of pottery. In addition, the rim shapes display a strong similarity to the rim shapes of matte-painted vessels and typical Western Sicilian matte-painted vessels, likewise dating to the 6th and 5th centuries. This suggests that the Piumata pottery produced locally only pretends to be old. In reality, it was made around the same time as it was discarded. Or in other words, something seemingly old was made new. We refer to this as traditionalism in the sense of an invented tradition, what is indicated also by the fine context of these vessels, to which we turn now. At the beginning of this talk, I mentioned the strong Greek influence at Montellato that emerged towards the end of the 6th century, particularly in the so-called late archaic house. Architecture, pottery, and dietary habits indicate the presence of a well-connected local elite enjoying a rather cosmopolitan lifestyle, including, for example, the consumption of imported wine, seafood, and fine sauces. And we do have archaeobiological evidence for this. And this elite was apparently also capable of recruiting specialists with a Greek background. This is indicated not least by locally made roof tile from the late archaic house, stamped and inscribed with the Greek name Xenon, most probably a Greek craftsman. On the one hand, this open engagement with the wider Mediterranean world through the consumption of certain material culture served as means of social distinction within the local environment. On the other hand, it also contributed to the formation of a rather Mediterranean elite identity. In this context, it is important to note that the cosmopolitan pottery and the cosmopolitan finds and features mentioned here can only be linked to activities within the late archaic house. And this cosmopolitan consumption space within the house stands in stark contrast to another consumption space outside the house, which served as a kind of open air festival ground. And in this outdoor area, we find almost exclusively pottery that can be classified as traditional or traditionalistic. In particular, Incisa and Piumata pottery, as well as handmade cooking pots. So in stark contrast to the interior, there are no vessels that are in any way reminiscent of Greek, Phoenician, or otherwise non-local vessels. And this situation reflects the two sides of the globalization coin. On the one hand, there's the desire to keep up with global trends and foster trans-regional contacts to maintain the rather precarious status of local elites. At the same time, however, it is necessary to clearly demonstrate strong ties to the local traditions. So what we see here is a production of locality, according to Arion Apadurai, which refers to a distant past free of modern influences for ensuring authenticity, a process that also involves the invention of tradition, according to Eric Hobsbawm, in order to create local identity. And it is precisely this process that we want to associate with the Piumata pottery, which refers back to a distant local past from an emic perspective. As said, this is indicated, amongst others, by its almost exclusively consumption in ritual contexts, which are free of any material that might point to a world beyond the local. Even though, from an ethic perspective, Piumata pottery is anything but a local tradition. Thus, the findings related to the area around the late archaic house can be interpreted as traces of the negotiation of specific social positions, sentiments, and identities for the purpose of maintaining power in a manner not unfamiliar to us from contemporary politics. Modernity and tradition, high-tech and Heimat, as the conservative German party puts it. And of course, I do not wish to draw simple historical analogies with this image of King Markus Söder, not least because, unlike the elites of ancient Montiato, his party enjoys anything but a precarious base of power, at least not in Bavaria. However, just how precarious the base of power was at Montiato is demonstrated by its clear disintegration from Mediterranean networks around the middle of the 5th centuries, accompanied by the ritual abolition of everything that might look Greek in favor of what was conceived as traditional. Moving back again from the level of consumption to that of production, we can see that the local potters of Montiato responded in different ways to different demands at the same time. In some cases, they adjusted their repertoire to a Mediterranean zeitgeist, while in others they satisfied more nativist needs. This illustrates that pottery production did not take place in a social vacuum, nor can it be viewed solely in an economic context. Equally, local production can't be explained in pure ethnic terms, since Greek and Phoenician vessels were also produced on site. Far more important to the question of why something was produced seem to have been local social dynamics, which are always connected to broader global phenomena. In the end, however, we can hardly investigate any of this if we do not know what was actually produced locally and what was not. Certainly not if we're talking about pottery. So let me things wrap up now. Based on data obtained by the support of NAA, we were able to outline the range of pottery produced locally at Montiato during the late archaic period. Not least due to its proximity to the maritime hubs of its Greek and Phoenician neighbors, connections to the material culture of the wider Mediterranean region began to emerge at a very early stage, while at the same time traditional values remained intact as traditions were even reinvented. It also became clear that local pottery production, whether traditional, traditionalist, or cosmopolitan, is always tied to the social practices of its consumption, which are shaped by by the relationship between the local and the global. So we are not dealing with a simple imitation of, let's say, Greek vessels because they are so beautiful or somehow culturally superior. Rather, pottery in all its diversity, ranging from complete adoption to partial adoption to the complete rejection of external influences, served specific needs embedded in the respective local situations, which in turn are not isolated from the immediate and wider environment. The local and the global are two sides of the same coin, expressed in both creativity and conservatism. In order to uncover such processes and dynamics, it is extremely useful to draw on archaeometric methods such as NAA in our case. After all, the question of what was actually produced locally ultimately forms the starting point for all further considerations. However, the greatest benefit only arises when we do not simply accept the data obtained as they stand alone and isolated, but integrate them into broader archaeological questions and larger frameworks. Act locally, think globally, so to speak. And that brings me now to the end of my presentation. I hope that I was able to explain our approach in a somewhat comprehensible way and that I haven't left you too bored or too confused. In any case, I would like to express again my gratitude for your attention and for the opportunity to speak here today. Thank you very much.
Thank you very much, Kai, both of you, and I would like Michaela to continue and to close the meeting.
I think even if we're a little bit over time, we
Yes,
should allow for a couple of questions.
yes.
Is there somebody out there who wants to ask one of the speakers a question? So just raise your hand. Oh yeah, Herr Mainzer, please.
Yeah, only very short. Thank you very much, especially for the second part, which shows the application of this technology with concrete results. And as I mentioned already in my introduction, I am very interested concerning the questions of indigenous peoples, because I think that is a very topical question nowadays. I must not deepen that. You all know the background, because our picture in history is sometimes dominated by the winners of the cultural evolution and the high cultures, and not the people who are between these evolutionary steps. Now, and your method is here empirical analysis of pottery and comparison of these different interaction of different cultural stages. My question is now methodological orientated. I mentioned it already also in my introduction, namely fingerprints. Every cultural influence has a fingerprint, chemical, physical, measurable fingerprint. So my spontaneous idea was concerning AI. Maybe it is too much to use AI, because it's a typical application of modern AI to recognize certain patterns and fingerprints in the data. And you have a distribution of data now at these islands, and then you can recognize the localization by fingerprint. That means pattern recognition with AI. That is modern machine learning. But maybe you only use conventional statistical methods, and AI is not necessary. Now, that's my question. Is that a perspective for you to use fingerprint recognition by AI, or is statistical analysis sufficient?
So this is a question to the archaeological we are not talking about chemical fingerprints.
Yes, my first part is more to you with the indigenous people, and my second part with the AI to your colleague of the first part.
Mm-hmm. Okay, so indigenous people. The problem is a bit that we don't have that's the other way around. In the Greek sources, the indigenous population of Western Sicily is called Illumians, but this is just a view from the outer side. We have no idea how they called themselves, or even if they feel something like that they have been bound together in somehow. So what we see is some similarities in material culture, but this does not allow us to draw a straight line or kind of border between different zones of Sicily. So I would rather expect that there's not as is the same for the Archaic Greek period, that there's not a sense of ethnic common belonging or something like that. So this is also the reason why we focus on the very local part. And if we focus on the local part, then we see that it seems not to be that important to express in some situations where are you from, but also to try to where you want to go to speak, in order to keep on with global trends. At the same time, for doing that, you have to balance this by drawing a more traditional line. So yes, so we are talking about an indigenous settlement, obviously, but I would put that rather into a broader Mediterranean framework.
Mm-hmm. And now the AI, would that be in the future a topic to apply for recognize typical fingerprints of certain cultural groups or peoples by a pattern recognition? That means by this kind of automated identification of fingerprints, or are you using conventional statistical methods such as in the past, and that may be sufficient for your purposes?
Currently, okay.
Yeah.
Ioannis, go ahead.
Yes, I would like actually to add to this because the reason is that I'm working on this subject, the last three years. In particular, yes, it is. The answer is yes. AI and especially complexity measures and like fractals as well can be used successfully as a fingerprint to identify various ceramics, and this can, or not only marble quarries and more, by analyzing the image of a thin section. Ioannis before Sterba, I mentioned about the microscopy, microphotographs from optical microscopy. Okay, if we take some thin sections of various sherds or archaeomaterials, I could say, of a particular scale, say 1 centimeter by 1 centimeter, or in micron scale, and we apply image analysis by various indices, fractal indices. Yes, it is possible to identify, and this is also effective, quick, fast, inexpensive, and one side does not need the great cost of instrumentation in a lab, like neutron activation, reactors, XRF, etc., etc.
Yeah, I see. Good, thank you.
I would like to add there, and maybe Johannes, you want to add something as well. There is a lot of tries now to use AI in interpretation of chemical patterns, because it's something it can do actually pretty well. You need to train the algorithms, of course, on your specific material, so it doesn't know just like that, but that's always the case. So there are a couple of things going on.
Good.
Yeah, my answer would have been similar. There's from where I stand right now, I don't see the necessity or the increased impact if I move to an AI algorithm instead of the algorithm I'm using already, because it's pretty straightforward. It's all numbers already. There's no wild pattern recognition. What you could imagine, and that's something we've been discussing since the late 90s, is to add to the chemical composition everything else we know about the sample, be it the color, be it the typology, be it whatever, and then use that for identification. And this is where AI would be much better than all the algorithms we can write by hand, because that's a lot more information that is a lot less clear and like numerically accurate. And this is something that AI is very good at handling, at this kind of vague information that we can't really pinpoint down, but AI can, because it has this huge parameter space in the back. For my work currently, I don't really see the need. It would be not a hard thing. It's an algorithm. You just plug it in and it spits out the same numbers it spits out right now.
Yeah. If it is sufficient and cheaper, we should use traditional methods. In the end, the result is important. Yes.
Thank you. So I would like to hand on. There's another question by Young.
Yeah, Jung. Actually, thank you very
Sorry.
much. I wanted to ask something about the macroscopically visible characteristics of your group YAT-B. Do the YAT-B samples have visible inclusions, or are they very, very fine? Or does both occur? Do you have vessels which are, let's say, as fine as Sigillata or Mycenaean pottery, I mean imported, or Corinthian fine wares? Or are they all tempered where you really can see the temper for the YAT-B? And the second question is, your Piumata pottery, is this only in YAT-A or does it also appear in YAT-B?
Good evening.
Hi.
Yeah, the tempering. So YAT-B group, yeah, there's different, and you can see it by the naked eye if you want. So anyway, within the group, it differs in relation to the wear. So among the matte painted pottery, which is the biggest share of this group, you can see also the temper, but it's quite fine. But it's not like let's say a Corinthian or Attic pottery. So you can see the temper, and we know due to petrographic analysis that includes also grog amongst other things. So, but taken together, all this YAT-B group, it is sometimes rougher, sometimes it's finer. And the second question was if there are Piumata pottery also in other groups. And yes, they are. We have YAT-A at least in YAT-A and in YAT-B, if I remember right. YAT-E is a rather small group without anything like that. And C, maybe one shot, but it's basically A with some in B.
Because I mean, I don't know if I should put this question, because actually we were working with Johannes on a paper these days, and we have YAT-B somewhere where it shouldn't be. So you're already expecting the question. It's coarse pottery, it's impasto pottery, so you really can see the inclusions. But typologically, it is by no means Western Sicily. It's Eastern Sicily. It's the area around Siracusa. It is incised Milazzese pottery. So you have Milazzese, which is a Middle Bronze Age pottery of Sicily. For the others, a Middle Bronze Age pottery of Sicily, 14th century, a little bit late 15th century. And at that time, Western Sicily produces Milazzese pottery, but never with these incised motifs. And we have several samples now We want to get more. So from typological reasons, from distribution reasons, I cannot imagine these pieces to be imported from Western Sicily. And so the problem emerges if the line that Johannes draws through different Sicilian groups is a phenomenon that impacts all of the island. And then we get problems with the petrography, because in the petrography, Pamela Fragnoli, who did the petrography of the Eastern Sicilian sherds, noted some differences with with those pieces that are Yat B and are from your side where the petrography is published. And this is a very tricky problem of chemistry and of statistical analysis when you know from archaeological points of view, which is quite rare that you come from that side and say something should be excluded. And it's the first time that I encounter such a phenomenon. We did this in kind of coarse pottery, this kind of coarseness at other sites. And usually what appears with the coarse pottery is that you get many chemical singles. And one group or maybe two groups, but not the opposite, that you have many groups which are all over the place, and you cannot find a correspondence. And the petrography is able to pinpoint geographical regions, to differentiate geographical regions, and the chemistry doesn't, because the chemistry seems to show that the same thing is found all over the place, in all of Sicily in this case.
Yeah, this is absolutely true. Yeah, but as for the Piumata pottery, as I said, it is not just that it looks like Piumata, but there's also these rim shapes that resembles the one that common from Western Sicilian mud painted pottery. So it is obviously a mix up, but it is quite a problem that we can't differentiate them chemically. But the good thing is that we can do by our traditional methods, more or less. But of course, this is something that we have to keep on working to find a solution for that kind of problem. Because I would completely follow you and would like to, what you, as you said, never should do, exclude something. But in that case, I mean, there is no Bronze Age evidence on Montillato, and so it seems to be impossible. Yeah.
And your Piumata is also not possible to be thought of as imported from the East, right? Because you said your rims are Western Sicilian, and it's not exactly like Piumata, apart from the chronological difference.
Yeah. It is not just the rims; it is also the shapes. We have very few shapes, and they are different. And some are wheel made by some are wheel made, and this is also something unusual in the West.
Guys, I'm sorry to barge in here. We are quite at the end of the session already, and I would like to maybe give Kidane the option to also ask his question.
All right, thank you. If we have some time, I would like to ask two questions. One is about, you know, they are from burial contexts, and there could be absorption, chemical transformation of various types, biogeochemical transformations, I mean. And how are these effects taken into account when you are doing the elemental analysis with NAA? Oh, and I like also to know about the sampling methodology. I saw some kind of driller. Is that a special one? How small samples were taken? Because there could be some effect from the weathering of the pottery material when you are doing the elemental analysis. The second question I have is already addressed. NAA can be complemented with petrography. It has been repeatedly mentioned, and probably you could get much more information about the binder, tempering materials, and so on, so that comparisons can be made in addition to the NAA result with this approach. You can compare, for example, samples from Monte Lato with Corinthian origin or Himerian one. You may not need to address all of them, but few samples could be selected and compared. And I wonder if you have done this kind of investigation along with the elemental analysis.
Maybe a quick answer to your first question. There's two things. When we sample, we use a sapphire drill. I might know actually. No, they're all in sharpening right now. It's a piece of sapphire.
I have one
yes,
here.
exactly. Wonderful. Yes.
So
that's a sapphire drill. It's a piece of artificial sapphire that is spanned into a drill bit and then can be used with an electric drill. The sapphire is very clean silicon aluminum oxide. So if we get some little pieces broken off into the sample, we only add to the silicon. So that's no big deal. Otherwise, it's very clear, very clean, and very, very hard. So it's easy to drill a sample. Sampling material, we take on the order of 100 milligrams, 150, maybe 80. Going below 50 is usually not a good idea because then measurement errors get very big. And with respect to general weathering, we usually remove the outer surface. So we drill away the first layer, 0.5 millimeter, whatever, depends on the sample shape, and then take the sample from the inside of the vessel. So that usually takes care of any weathering that might occur on the outside. In general, if we have nice chemical groups, then we have nice chemical groups. So if there's any, if a single vessel happens to be chemically altered in deposition, then this will just not fit into the group. And then we can start to discuss if it should fit into the group and see if there's anything we can do. But since we have nice group, there's no real question about weathering in this case.
Yeah, maybe to
go ahead.
Maybe just something to the second questions. We didn't apply petrography because we were just interested in the provenance of the vessels and not so much in the recipe and how things or the chain operatoire and things like that. What is also a very interesting point, but this is not nothing that we did. This has been done by colleagues at Montellato, Giuseppe Montana, and some others, and they used an approach, a combined approach, petrography and ICP or MES, I think, if I remember right. And we have both sampled a handful of the same vessels, and what turns out is that they are local. Even from the petrographic side, of course, they have some more local groups than we have due to the inclusions and of the recipes. But basically, we came to the same conclusion: what is local and what is not. So yes.
Thank you. Are there any other pressing matters somebody wants to raise? No, if not, I will have to bother Johannes at some other point, because I would have a couple of questions on the statistics you used and how if they're yours or if they're more used in NAA, and how we could adapt them for PXRF, because I've heard of them, but I've never seen, especially the Bayer-Mommsen correction, really be applied to data in a broader sense. So, but unless you want to.
No. I think it goes beyond the scope of the next hour. But interestingly, Hans Mommsen started out in XRF. He just doesn't talk about it, but he did. So I am fairly certain that the statistical measures can be applied to any set of data, but it's not as straightforward as for NAA because it's been specifically developed for NAA. So if we move to a different method, we need to rethink how errors are produced, which elements are good, which are not so good, which are significant, and so on and so forth. So it's a bit more complicated than just plugging it into the algorithm and seeing what happens. I tried this, by the way, not with XRF, but with prompt gamma neutron activation analysis, which is again a different beast. So yes, I mean, again, we're not that far away. just give me a call.
Yeah.
We get together and we play around with it a little bit. It's not that
Yes,
hard.
I think you already have some PXRF data we could use, you know.
Sure.
Yeah, that would be lovely. So
Yeah.
we might could also consider finding a training opportunity for others when we figured out how things work.
Yeah, sure. That would be very interesting.
And now we have it recorded. So now you know, sorry for that.
Fine.
So thank you, everybody. I just want to quickly mention that we have the next colloquium on the 28th of May. So we would be happy to see you all there. We will then focus again very specifically on PXRF and on the applications. So thank you very much, everybody, for your time, for the discussion, and have a good evening. Enjoy the free day tomorrow if you're lucky to have it.
Okay.
Good.